Here we are looking at example 2 from our 1.4 set of notes. We're asked to graph the following rational function and determine where, so we have to determine where is it continuous. Now, just looking at the top and the bottom, if you were to Now, just looking at the top and the bottom, it looks like we can go ahead and factor out our top. So when we do that, we have x plus 3 times x minus 1 all over x minus 1. And we notice that our x minus 1s can end up canceling out with one another. So as a result of that, we'll actually end up with a hole instead of a vertical asymptote. So for our hole, we have x minus 1, and that's equal to 0. To go ahead and try and solve for what x value would that actually happen at. Well, when we add 1 to both sides, we see that x just comes out to be 1. And now we can go ahead and throw that into our simplified version of the function to determine what is that y value. So for the y value, not the y-intercept, just the y value specifically for this hole, we end up with y is equal to 1 plus 3. So it looks like it just comes out to be 4. So we should see a hole specifically at 1, 4. Going ahead now and graphing that, we have a hole at 1, 4. And there is our hole. And we also have our simplified function coming out to be y is equal to x plus 3. Well, that's just a line with a slope of 1 and y-intercept of 3. So we'll go ahead and graph what that looks like. And so it's going up 1 over 1 every single time. We should see our graph do something like this at least. And the question is determine where is this thing in fact continuous? Well, when we're talking about continuity, we notice that the first criteria would fail, right? Because f of a, specifically at 1, is not, there's no point here. And as a result, this thing is not going to be continuous throughout the entire interval from like negative infinity to positive infinity. But our goal is to determine where is it continuous. Well, the smallest thing that x can be, and that it is in fact continuous, would be negative infinity. They are defined all the way out here as you go out towards negative infinity. So all these different f of a's are in fact working for this function. And then finally we approach that x value 1. In other words, when we throw in 1 into that function, we do see that undefined hole there, causing that discontinuity. So as a result, we're going from negative infinity to positive 1, and then right after 1, we kick back in, and all these other points also work, and they do exist. And so pretty much f is continuous by saying this statement. F is continuous for all real numbers except for x is not equal to 1. Even if it's criteria 2 that the limits do exist for any particular a value that you might choose, the left side, like let's just say we went with this particular a value, the left side is matching with the right side, so that's fine. It also fits criteria 1, 2, that point does exist, and then they do end up meeting at the same spot, fitting criteria 3. For this one, this is the only value, x value, that will not work, 1. So we've gone ahead and determined where is this thing in fact continuous. Here it is, between negative infinity, comma 1, and then 1, comma infinity. Now, a lot of times, when we start talking about continuous function, it's really, really similar to that idea of the domain. So a lot of times when you see like those vertical asymptotes, that's specifically where you're not going to see that continuous function. Likewise with the holes. Okay. So again, though, that is example 2 from our 1.4 set of notes.